I'm Jennifer French. I work in the math department, and I have been involved with a lot of residential projects, but the thing that I'm going to talk about now is a project that we started for our calculus class that we actually released first as a MOOC and are only now using residentially for the first time.
Yep, so I'm Martin Segado. I'm a graduate student in mechanical engineering. I got into online education through TAing actually for mechanical engineering courses that were released as MOOCs, and worked with Jen last year to help develop the sketching tool for this calculus course.
When we decided to make calculus as a MOOC, the biggest issue that we had was that sketching was a really big part of our objectives for students in a calculus course. There's a lot that goes on. We want them to understand the mathematical language and the symbols. We want them to understand how these are represented as curves and functions in the plane, and we want them to understand the physical meaning behind them and to be able to move fluently between all these things. And so we really wanted students to be able to enter sketches into, just draw them into the platform, because otherwise, we felt like we actually could not teach calculus at all. And there's also a lot of research that supports this. We know that expert problem solvers frequently use sketches in many, many fields all over science. Oh, no.
Oh.
It was fine for a second, and then, no, it was never fine.
Might have been the...
I'm going to just take this thing off.
Yep, that's a good idea.
Even this page is missing the left-hand side.
Yeah. Oh.
Just try hitting present again, see if it works.
Let's see if I can first make it... We tested it on my computer first, I'd like to point out.
There we go.
Oh,
Yeah,
Yep.
that's better.
that is indeed better. Lovely. Yeah, indeed.
The other thing, so the other reason we wanted them to actually generate sketches is that we know that this is actually a higher cognitive skill to generate something and to construct something yourself versus recognizing other people's sketches through something like multiple choice. And ETS has actually done a lot of research showing that actually there are skills that cannot be adequately measured using multiple choice. And we really believe that sketching is one of them. The other issue is that we really wanted to be able to automatically grade sketches. And this obviously was important for our online students, but it was also important for us thinking about our residential students here on campus. And one of the reasons is that typically these are graded on paper, they're submitted, there's a delay in the feedback that the student gets. If they even look at that feedback, it may not be very detailed. And whereas with the automatically graded sketches, we can provide immediate targeted feedback on where the sketch is going wrong, and we can give them multiple attempts so that they can actually correct their mistakes and get it right, which is ultimately what we want. We want them to get it right, and we want them to figure out where their mistakes are and fix it right away. I'll just give you a brief demo of what the tool looks like. You see that it has these plug-in tools at the top, like a function, a vertical line asymptote, a horizontal asymptote, and various points, and that you can drop them all in and sketch. There's some automatic smoothing that happens in 2 different levels. First, it smooths a bit just as you're drawing, and then it actually smooths the final result by fitting everything to cubic splines, which are what we actually use. That's what we pass to our grader to do the analysis for the grading.
Okay. So, of course, you guys aren't here to see bullet points, I'm sure. Pretty pictures are much nicer. So we actually deployed and ran this in a course, which finished back in December.
No, so we ran it in the first course that ran over
yeah.
the summer. It started in June, but we actually started with a prototype of the tool, and about halfway through, launched the version that you just saw, and then that course ended in August. And then we have a second course that is running right now. Actually, it was supposed to be over today, but due to an edX timer bug, we extended the
Yes.
deadline to tomorrow. So it'll be over very soon. And we used the sketching tool there as well.
Yeah. So the results that we have over here from some of the problems that we ran in the first of those two courses. We deployed a total of 13 different problems using the newest version of the sketching tool. We had 870 odd learners interact with this in some non-trivial way, so submitting an actual graph. This is not including the course staff as well. And over the 13 problems, they actually generated a total of just over 8,000 graphs. About 89% of them were correct by the last attempt. That varied depending on the particular problem, but overall people seem to be getting these right, which is encouraging. And people seem to be getting them right in a reasonable number of attempts, typically. So generally we saw 2 or 3 attempts for people to get them correct. Here you can see the actual distribution of number of attempts for the different problems. So along the top row and the second row, we have some of the practice problems that we gave them, or exercises, as well as some of the homework problems. The blue bars on the right of each of these graphs are students, or the distribution for students who eventually got the problem correct. The much smaller red bars on the left are the distributions for the students who never got the problem correct. So you can see overall, most people eventually got it correct. A lot of people got most of these correct in a single attempt, which is really wonderful. Some of the problems were considerably harder. So, for example, this problem, you'll notice very few people got it correct on the first attempt. A lot of people got it on the second. Several people lasted longer, and these poor souls up here apparently submitted 10 or more tries before they got it correct, which is really quite impressive. Another conspicuous feature here is you'll notice there are no attempts above 5 for the final. This is because we didn't limit the number of attempts for most of the problems, but we did limit them to 5 attempts for the final. So you notice also for the final, there is a much higher fraction of incorrect submissions because we had that limit on the number of attempts and because the stakes were considerably higher. And also the people who did eventually get it wrong used up all of their attempts, as you can see. Can look at the average attempt distributions for exercises and homeworks as well. And this shows more or less the same picture as the other ones. Typically, students would get this correct in somewhere between 1 and 3 attempts. There's a bit of a long tail up here with some students taking 7, 8, 9, 10 or more attempts to get it correct, but eventually getting it correct. And on the incorrect side, we actually see a similar pattern. So a lot of students tried it once and then gave up. Several students tried it a few times, and the numbers dwindle as you go higher up. And again, we have a few poor, frustrated folks at the very top who tried 10 or more times before finally giving up and not getting the answer. Thankfully, the proportion is quite small, although it would be ideal to improve that in the future. Here's the corresponding picture for the final exam. In this case, most students got it correct probably within the first couple of attempts. Most students who never got it correct used up all of their attempts, which is pretty much what you would expect. There were still some students who just tried once even on the final and then gave up, or twice and then gave up, which is interesting, but they're a fairly small percentage. Promised pretty figures, so here are some pretty figures. Since we do have quite a few submissions for each problem, one of the interesting things that we can do is simply overlay them, give each submission itself some translucency, and then we can kind of look at the aggregate to see if there are any patterns there. This is one of the easier problems where we're asking them to draw a quartic function, I believe. You can see there are some things that are fairly tightly constrained, so a lot of people will get the critical point location here exactly at x equals 1 or very close to it. And then there are other things that pedagogically we simply don't care about. We don't care about the exact position of the tails of their function. All we care about is that it's generally going up. There are also much more complex problems that we gave them. This is one of the harder ones that we asked them to draw, and yet still a significant chunk of our users were able to eventually get the correct submission, as you can see. So in this case, we have multiple asymptotes, both vertical and horizontal. We have critical points around here. We have inflection points as well, and then the function itself that goes between all of these. So this one you can go for because it's kind of an interesting, unexpected result that we saw.
So one of the things, some of these problems, there's a grid here because we graded them on a grid, but a lot of the problems we actually are just grading qualitatively, so we didn't give the students axes to see necessarily, although there was a grid.
Yeah. Nor did we expect exact numerical results for some of these. We just wanted the general shape.
So, maybe I missed it, but what's correct?
All of these are correct
No.
that we're showing.
Okay.
Pedagogically, you mean what's correct?
No, I mean,
What were you looking for?
you're not showing the incorrect ones.
Oh, we will.
What
Well,
makes them correct?
oh, I see. Each of these has its own associated grading script. The scripts look for different things depending on the problem. Typically, we're checking for the location of critical points. We're checking for the number and position of asymptotes. We're checking the slopes of the function in different region. Occasionally, we're checking if the function passes through a particular point. And very occasionally, we also check curvature.
Yeah. So in this problem, we're checking things like where is it increasing, where is it decreasing, especially with respect to things like the asymptotes and with respect to the labeled critical point. And so that's actually the important feature, is that once the student labels a point as being critical, that is actually essential to our grading script because we grade with respect to that labeled point. And
The student labels points being critical, so each student gets to label what they consider critical?
yes, and those are those dots that you actually see here. This is the point that the student labeled as critical.
Yeah. The advantage of that is that it lets us ask qualitative questions. So we can ask them to draw the general or to sketch the general shape.
It's just not a trivial problem to grade those things at all.
It is not.
Yeah, there's,
But actually, we find that having them drop the point makes it easier in many ways. That's part of why we did, that's why we have the multiple tools, is that we find that just grading something as, is this asymptoting, like, that's essentially impossible. It's very, like, these actually all look pretty nice, but, you know, you could grade something, you could draw something like this over here, and that's technically asymptoting to the correct things. And so it's much better if they just tell you, that's my asymptote. And so that's what we chose to do. But the interesting thing about this is that you actually see that by and large, when people chose where to drop their critical points, you see a lot of people choose along grid points, which is something that you would expect. If you're going to pick a random point, why not pick something on a grid? Except then you have this one random point.
and this is a concentration of points, which is why it's showing up brighter.
So in these problems, this was early on in our release. We had just released the tool. And so we actually gave them 100 attempts, and we allowed them to see the answer whenever they wanted. So you may guess this, but this is where we placed it in our solution.
So anyway, this was an interesting feature. It seems that there's a good chunk of people who were just looking at the solution and exactly copying it.
Yes.
Where people could have multiple accounts.
Yeah, when we first released the new version of the tool, and that it was halfway through the course, we were a little bit hesitant to put too much weight in it and put too much emphasis on the grading. And so that's why we allowed students to be able to see it and just cheat, basically, because we were like, give us feedback. If you have a correct answer and it's wrong, we need to know about it. We're going to make improvements. We'll fix it in real time. Tell us. And I mean, all of the edits that we made to the grader were from people being like, hey, my solution is not right. What's wrong about it? And actually, I could go a couple slides back. Here you see an artifact. I don't know if you can see it. There's a faint line right here. And this is from a change I made in the grader script to reduce my restriction on counting the number of asymptotes, because it turned out that on some computers, when they dropped an asymptote, it was actually dropping 2 and right over each other, and so I couldn't count them the way that I wanted to, and we fixed that bug. But this grader had an artifact where I had not then gone back and fixed it. And also, I don't like to take away points after I give them, because I'm soft like that. But
yeah. So you had asked about some of the incorrect answers. The incorrect answers.
Could you give us the question?
Certainly. So there were a few questions, I think. Do you mean the question that's up here?
How did you ask that?
How did you ask this one?
Well, of course.
So I suppose we can, if we have a few minutes
this
at
one
the end, we
we
can
gave
pull up the
that.
actual
Yeah,
page.
there are a couple different ways that we would ask questions. Basically, they had 3 formats. Either here's the formula for a function, sketch the derivative, or here is the function's derivative and second derivative, sketch the function, or here is a sketch of the function, sketch its derivative. And these, I think, this one in particular was, here's the function and its derivative, and sketch it. This was early on, so we were really nice to them. We did all the hard work for them.
Yeah. We can pull up, if people are interested afterwards, we can pull up some of the live MOOC content after this talk and show you what it's like. So incorrect submissions. In general, these plot much less cleanly than the correct submissions. Some of them are all over the place. It helps somewhat to sort them or to categorize them by the feedback that we gave. So in this case, we're showing all of the incorrect submissions for one of the final problems, where we gave the feedback, what is the relationship of your function to the horizontal asymptote? So in this case, you can see there's a clear conceptual error that students had over on the left-hand side of the graph, where all of these students continued their function above the asymptote instead of asymptoting from underneath, which is the correct response. There was another one which showed some fairly clear clustering. Here we gave the feedback, check the location of your horizontal asymptote. And while there are a few that are kind of scattered throughout, like up at +2 and -1, there was a significant cluster of students who submitted as an incorrect answer an asymptote at 0. So we can get some interesting information about misconceptions. In general, this is much harder, though, to look at than the correct submissions. So one of the things that we hope to do in the future is look at perhaps some machine learning clustering techniques to see if we can extract some of these features.
And then we also want to rewrite our grading scripts in order to make sure that we're giving the right feedback at the right time based on the correct misconception.
So a few future directions. One of them I just mentioned is looking at some clustering analysis of the data. Another thing that we are thinking of doing is looking at automation for the grading scripts. So currently, the different criteria that we're checking, the instructor specifies through a Python script and can go through several conditions where they say, make sure the graph is increasing in this location, give this feedback if not, make sure there's a critical point here, give this feedback if not. However, for a lot of classes of problems, such as rational functions in calculus, it might be a lot more convenient to simply have a semi-automated grader which we can feed a function and tell it to check for slopes, curvatures, and asymptotes, and simply have it generate all of the criteria necessary. Mechanical engineering, which is my department, there are a lot of possibilities for this as well. For example, we could have beam problems where the instructor feeds in a beam with particular forces, and the greater criteria are automatically generated for an axial force diagram, for example. Eventually, this opens up a really exciting possibility, which is to automatically generate randomized sketch problems. So for mechanical engineering, again, we might have a beam and simply drop forces on it at random with random magnitudes and directions and have the student sketch the graph in response. And this is great not only for things like preventing cheating in MOOCs, but it's also absolutely wonderful for students because they now have unlimited practice problems in a particular class of problem. So that's a very exciting possibility. There are a few things that we want to do with the tool itself. One of them is work on keyboard accessibility and accessible drawing tools in general. Using the mouse or touch or pen input seems to be working fairly well for a lot of our users, but there are users who simply will not be able to do that due to mobility impairments or vision impairment. So that's something that we hope to improve. And then finally, the ultimate plan for this is hopefully within the next few months or so.
Better be.
Yeah, to open source it and disseminate it. So we have folks at a few different universities who are interested in using this, and if any of you all are, please let us know. So, thank you very much. If you have questions, please feel free to email us, grab us after this talk. Jen has a website up with a live demo of this tool if you want to go and try to sketch a rational function. Use Wolfram Alpha. If you can't figure it out, that is perfectly fine.
So you mentioned three types of problems you'd ask. Here's a function, sketch its derivative, or types of things. One of the issues I've found repeatedly in my freshman physics courses is that students have trouble sketching a function given that function. Is there a reason that you...
Oh, we do that
Oh,
too
you do that
also.
as well? Okay.
Yeah. Actually, the final exam problem that you saw, one of the final exam problems where they had the incorrect behavior of the asymptotes, let's just go back to it. This actually was a sketch this function problem. And we had several of those as well, though not in the other data that you saw. And so the issue was exactly that they didn't understand the behavior as it went towards negative infinity.
Can you grade things like the integral or the derivative of the function that they produced?
Yeah, we don't have that data here because it was a bit confusing to look at, but that's actually one of the problems that we had was actually sketch the derivative and the second derivative, and we can grade it all together.
So depending on the problem, we might ask for that explicitly.
If you,
Oh.
if they drew a figure, the problem might be write a sketch of the acceleration such that at the end the velocity is so and so. So you're really asking, you want to grade the integral of the curve that they submit.
Oh yeah, we can do that.
Yeah.
Especially
Well,
if you give it an initial value, or like a point to go through. That makes it even easier.
Well, yeah, and it's also maybe much harder to make a derivative grader because that increases instabilities.
So actually, I
I
think
think
at
it's
the
the
moment,
I think
at the moment the one that we're doing is the derivative, the slope grading. So.
Oh yeah, well we are grading. You mean what the grader is doing, or what? I think
what
you.
the grader's doing, I think.
Yeah.
Okay.
Oh, okay. Yeah, no, we're looking at slopes. We are looking at the derivative
But
mostly.
the data is there to look at the integral too if we wanted to.
Because what we're actually passing as the data is a collection of splines, cubic splines that we actually have all the information about that we know everything about the splines.
Would it be possible Possible to do implicit function plotting, like x squared plus y squared equals 1?
Working on that right now as I'm making some polar graphing problems. It is possible.
Thank you so much, Jennifer and Martin.